Hi students, welcome to Sunil's tutorial. I'm Sunil Nirvani and today we'll be doing this chapter called as atoms, molecules and nuclei. Let's see this. Let's take down some guys. The energy of an electron in ground state. I think we've done this some. Yeah.
The next
Next. The energy of an electron in ground state is minus 13.6 electron volts.
So we did this.
Yeah, it's the next sum. The energy of an electron in the ground state is minus 13.6 electron volts. Calculate Rydberg's constant. Calculate Rydberg's constant. Calculate Rydberg's constant and the wavelength of the second member of the Balmer series and the wavelength of the second member of the Balmer series. Also calculate the energy in the electron in third orbit. Also calculate the energy of the electron in the third orbit. Now guys, we know that energy in the nth orbit is minus me4 upon 8 epsilon 0 square n square h square. Now for ground state, n is equal to 1, therefore energy in the first orbit is minus me4 upon 8 epsilon 0 square h square. Right? Now Rydberg's constant. Rydberg's constant is given by the formula me4 upon 8 epsilon 0 square ch cube. Right? Now, if I divide the two equations, I'll get r upon E1 is nothing but minus 1 upon ch. So in which case, I'll get r is minus E1 upon ch. Right? Next, once I have this, then I can say that r is minus E1 upon ch. I know the value of c, which is 3 into 10 raised to 8 meters per second. I also know the value of Planck's constant, which is 6.63 into 10 raised to minus 34 joules second. Right? In that case, r is minus E1 upon ch. You have the value of c, you have the value of h, you also know E1. I could say that E1 was given to me as in the sum as minus 13.6 electron volts. Convert that into joules. 13.6 into 1.6 into 10 raised to minus 19 joules. So thus that will give you your Rydberg's constant minus E1 upon ch. Once I have the value of r, then I can find out, they've said for Balmer series. Now for Balmer series, P is equal to 3. Right? Sorry, for Balmer series, P is equal to 2. Right? Now, once I have this, they've asked you to find out, calculate Rydberg's constant, calculate the wavelength of the second member of the Balmer series. Now, if P is 2 for second member, n will be equal to 4. First member n would be 3, for second member n will be 4. So in that case I can say that 1 upon lambda is r, 1 upon p square minus 1 upon n square. Right? Now once you have this, then you can get the value of lambda from here. You will come to know the value of the wavelength. Next, they have also asked you that calculate the wavelength of the second member. Also calculate the energy in the third orbit. Now energy in the first orbit is given to you. They've asked me to find out the energy in the third orbit. We know that energy in the nth orbit is inversely proportional to 1 upon n square. So I can therefore say that energy in the third orbit upon energy in the first orbit is n1 upon n3 the whole square, where we know that n1 is 1 and n3 is 3. Fine. Now this can be written, you will get your answer of the energy in the third orbit. So I can therefore say that lambda is nothing but 4862 Armstrong units, and energy in the third orbit is minus 1.511 electron volts. Right? Next, the shortest line, the shortest wavelength line in Lyman series, the shortest wavelength line in Lyman series, the shortest wavelength line in Lyman series is 912 Armstrong units. Is 912 Armstrong units. Calculate the wavelength. Calculate the wavelength of the shortest wavelength line in Balmer series and the longest wavelength line in Paschen series. Now, Lyman series is going to be 1. Now they are saying that the shortest wavelength line in Lyman series. Now for the shortest wavelength, n should be equal to infinity. Once I know n is infinity, then I can say that 1 upon lambda is equal to r 1 upon p square minus 1 upon n square. Right? So I know the value of lambda, I know p, I know the value of n. Right? So in that case, I will get the value of here. I'll come to know the value of Rydberg constant. Using this, I'll come to know the value of Rydberg constant because lambda n is given to me, p and n are given to me. Next, the second part of the question for Balmer series. Right? For Balmer series, I can say that p is equal to 2. Right? Now, they've asked you to find out for Balmer series the shortest wavelength. Now, for shortest wavelength, n is going to be equal to infinity. Right? 1 upon lambda b is r 1 upon p square minus 1 upon n square. So I'll come to know the shortest wavelength for Balmer series. Next, they also asked you to find out, calculate the shortest wavelength for Balmer series and calculate the longest wavelength for Paschen series. They've asked me to calculate the longest wavelength for Paschen series. Now I can say for Paschen series, I can say that P is equal to 3 for longest wavelength. Since P is 3, N should be equal to 4. I can say 1 upon lambda P is R 1 upon P square minus 1 upon N square. should be able to get this answer, right? The answer for this sum should be Balmer series is 3648 Armstrong units. Passion series is 18,761 Armstrong units, right? Next, compare the shortest wavelength of Balmer series. Compare the shortest wavelength of Balmer series with that of Passion series. Compare the shortest wavelength of Balmer series with that of Passion series. For Balmer series, P is equal to 2, right? Now, they said that for shortest wavelength, n will be equal to infinity, right? Now, for Balmer series, I can say 1 upon lambda b is r 1 upon p square minus 1 upon n square, right? So you will get your answer in terms of r. Leave that answer in terms of r. Do not substitute the value of r. Okay. Then they have asked you to compare the shortest wavelength of Balmer series with that of Passion series. Now for Passion series, I can say that P is equal to 3. Right. Once I have the value of P, I can say for shortest wavelength, n is equal to infinity. So I can say 1 upon lambda L is R 1 upon P square minus 1 upon N square. So I'll come to know this is not Lyman, this is Passion series. Okay. Now they've asked me to compare the two, right? So I can say that divide the two equations. If I divide the two equations, I should be able to get that answer. Call this as 1, call this as 2. Divide equation 1 and 2. Both the answers you would have got in the form of R, right? So you will get 1 upon lambda Balmer upon 1 upon lambda Passion is going to be equal to Balmer is R upon 4 and this is R upon 9, right? So in that case you should be able to get this answer, the ratio of Balmer to Passion series. Just reciprocate and you will get your answer. Next, take the next one please. The wavelength of H alpha, for Balmer series is 6,560 Armstrong units. 6,560 into 10 raised to minus 10 meters. Calculate the wavelength of the first line. Calculate the wavelength of the first line of Lyman and Passion series. For Balmer series, we know that P is equal to, they've asked you H alpha, okay. P is equal to 2. Now what do you mean by H alpha? H alpha means the first line in Balmer series. right? H alpha is the first line in Balmer series. If it is the first line in Balmer series, in that case n has to be 3, right? Then I can use the formula 1 upon lambda b is r 1 upon p square minus 1 upon n square. So you will get your answer. Lambda b I know, p square I know, n square also I know. So I should be able to get the answer. What do they ask you to find out? Calculate the wavelength of first line of Lyman series. Okay. Now from this I'll be able to get my value of Rydberg constant. Okay. Now for next thing they've asked you to calculate is Lyman series. For Lyman series, we know that P is 1 for first line, n will be equal to 2, so 1 upon lambda L will be R 1 upon P square minus 1 upon n square. So you will come to know your first line of Lyman series. Next they have asked you to find out the first line of Paschen series. For Paschen series, I can say that P is equal to 3 for first line, n will be equal to 4, so 1 upon lambda P is R 1 upon P square minus 1 upon n square. So that is what will be your answer. Now you can say that the answer for this sum should be lambda L. Lyman series should give you an answer of 1215 Armstrong unit. Next, Paschen series is 18,740 Armstrong units. Right? Next. Next sum, the wavelength of H alpha line. The wavelength of H alpha line in Balmer series the wavelength of H alpha line in Balmer series of hydrogen spectrum the wavelength of H alpha line in Balmer series of hydrogen spectrum has a wavelength of 6,560 Armstrong units. Calculate the wavelength of H beta. Calculate the wavelength of H beta. Calculate the wavelength of H beta. Now, for Balmer series, I can say that P is going to be equal to 2. Now they said that H alpha. What do you mean by H alpha? H alpha means the first line. H alpha is the first line of Balmer series. If it is the first line, then n will be equal to 3. So in that case, I will say that 1 upon lambda is R times 1 upon P square minus 1 upon n square. Right? So they've given you the value of n, p, lambda b, so I'll get the value of Rydberg's constant. Okay. Now they've asked you to find out H beta. For H beta. H beta means the second line, guys. Remember, H alpha is first line, H beta is second line, H gamma is the third line. So H beta is the second line of Balmer series. So n will be equal to 4. So I can say 1 upon lambda b is R 1 upon P square minus 1 upon N square. Rydberg constant you already found out from the previous equation. You can substitute that here. So you will get your answer. So you will get the answer for this sum to be 4859 Armstrong units. Next, take on next one please. The H beta line of Balmer series. The H beta line of Balmer series. The H beta line of Balmer series of hydrogen atom the H beta line of Balmer series of hydrogen atom has a wavelength of 4860 Armstrong units. Calculate the wavelength of H alpha. Calculate the wavelength of H alpha.
Calculate the wavelength
of H alpha. Calculate the wavelength of H alpha. Replica of the previous sum, guys. It's only that they've given you H beta and they've asked you to calculate H alpha. If you've understood the previous sum, you should be able to solve this sum in a similar manner. I'm not showing you how to do it. The answer for this sum should be 6561 Armstrong units. Next, take on next one please. The second member of the Balmer series, the second member of the Balmer series of hydrogen atom the second member of the Balmer series of hydrogen atom has a wavelength of 4861 Armstrong units. Sorry, 4861 Armstrong units. Calculate the wavelength of the third member. Calculate the wavelength of the third member. Calculate the wavelength of the third member. Now, guys, for Balmer series, we know that P is going to be equal to 2. Now they've said second member. Sorry. For second member, N will be equal to 4. Right? That's the second member of the Balmer series. So I can use the formula 1 upon lambda beta is R times 1 upon P square minus 1 upon N square. From here I'll get the value of R, I'll get the value of Rydberg's constant. Now they've asked you to find out the value of the third member. Right? For third member, N will be equal to 5. So I can say 1 upon lambda gamma is R times 1 upon P square minus 1 upon N square. Right? So you will get your value of lambda gamma. Answer for this sum should be lambda gamma is 4340 into 10 raised to minus 10 meters. Next, take on next sum. The energy in a photon is 2 electron volts. The energy in a photon is 2 electron volts. Calculate its frequency and wavelength. Calculate its frequency and wavelength. Calculate its frequency and wavelength. Now we know that E is equal to hv, where v is the frequency. We'll write it this way. So I could say that v is equal to E upon h. Energy I've already converted into joules, so I'll come to know the frequency. Once I know the frequency, then I can find out the wavelength. I can say lambda is equal to c upon v. C is 3 into 10 raised to 8 meters per second upon v. You already found out the value of v from here. You should be able to get the answer. Answer for the sum should be frequency is 4.827 into 10 raised to 14 hertz, right? And wavelength is 6215 Armstrong units, right? Next, find the mass of the proton. Find the mass of the proton of radiation Find the mass of the proton of radiation having a wavelength of 5000 Armstrong units. Having a wavelength of 5000 Armstrong units. Now let's try to see this. They have asked you to find out the mass of the proton. Now we know that E is equal to hv, h into frequency. Now frequency is nothing but velocity upon lambda. So I can therefore say E is equal to c upon lambda. But by Einstein's equation, E is also equal to mc square. Therefore, I can say that mc square is equal to hc upon lambda. C and square gets cancelled. So in that case, I will get m is h upon c lambda. M is equal to h upon c lambda, right? You know c, you know h. H is Planck's constant. C is the velocity of light, where I can say that h is 6.63 into 10 raised to minus 34 SI units, and c is 3 into 10 raised to 8 meters per second. Lambda they've given you, so you should be able to get the answer for this. Answer is 4.42 into 10 raised to minus 36 kgs. Next, take down next sum please. Calculate the percentage increase in the rest mass of the electron when it is moving with a speed of 0.8 c, where c is the velocity of light. Now guys, if v is equal to 0.8 c, then I can say that v upon c is 0.8, square both the sides, v square upon c square is 0.64. Now let us assume that let m0 be the rest mass of the electron. If m0 is the rest mass of the electron, then while moving, the mass of the electron will be m0 upon square root of 1 minus v square upon c square. We have already found out the value of v square upon c square. you can find out the ratio. Here you will get this as m is equal to m0 upon square root of 1 minus 0.64, which will be nothing but m0 upon square root of 0.36, which is m0 upon 0.6, right? So in that case, what will be the increase in rest mass? Increase in rest mass, that's your delta m, will be mass when it is moving minus the rest mass. So m we found out is m0 upon 0.6 minus m0. So in that case you will get this as 10 m0 upon 6 minus m0. I'm getting rid of the decimal. So 10 minus 6, that is 4 m0 upon 6, right? Once you have this, then you can say that this is nothing but 2 m0 upon 3. Once I know the increase in the rest mass, I can find out the percentage increase in the rest mass. Percentage increase in rest mass is delta m upon m into 100. I've already found out the value of delta m upon m into 100. M can be written as m0 upon 0.6, and you can substitute, sorry, this should be m0, rest mass, no? Delta m upon m0 into 100, right? The answer for this sum should be 66.67%. Next, take down next sum please. What is the de Broglie's wavelength? What is de Broglie's wavelength of a particle moving with a speed of 2 into 10 raised to 6 meters per second if it is, first part of the question, an electron, second part of the question, proton, third part of the question, a 1 kg ball, if the mass of the proton is 1.675 into 10 raised to minus 27 kgs. Now, we know that de Broglie's wavelength lambda is equal to h upon mv, right? Now, they've given you that mass of the proton is given to you. Okay, now the first part of the question, what will be de Broglie's wavelength if the object is an electron? So for an electron, we know that mass of the electron is nothing but 9.1 into 10 raised to minus 31 kgs. Straight apply the formula. Lambda will be h upon me upon v, me into v, sorry. H is Planck's constant, which we know by heart is 6.63 into 10 raised to minus 34. Mass of the electron is known to me, velocity is known to me. I should be able to get this answer. Second part of the question, for a proton, mass of the proton is given to me 1.675 into 10 raised to minus 27 kgs. That's my mass of the proton. So in that case I can say lambda is h upon mass of the proton into velocity. Mass of the proton, h is Planck's constant, velocity is given to me, I should be able to get this answer. Finally, for a 1 kg ball, mass will be 1 kg, so lambda will be h upon mv. Mass is given to you as 1 kg, you should be able to get that answer, right? The answers for this sum should be: wavelength of the electron is 3.64 Armstrong units, wavelength of the proton is 1.978 into 10 raised to minus 13 meters, and wavelength of the ball should be 3.3125 into 10 raised to minus 40 meters, right? And those should be the wavelengths of the different objects. Next, take down next one, please. What is the speed of a particle? What is the speed of a particle? What is the speed of a particle that has de Broglie's wavelength? That has de Broglie's wavelength of 0.3 nanometers. Of 0.3 nanometers if it is, first part of the question, an electron, second part of the question, a proton. First part of the question, an electron, second part of the question, a proton whose mass is 1.675 into 10 raised to minus 27 kgs. Now guys, de Broglie's wavelength is given by the formula h upon mv. Now first thing, for an electron we know that mass of electron is nothing but 9.1 into 10 raised to minus 31 kgs, right? Once I have this, then I can find out what does it ask me to find out? Velocity. So I can say that velocity is h upon m lambda. Mass of the electron is known to me, me is known to me. H is Planck's constant, which is 6.63 into 10 raised to minus 34 SI units. So I should be able to get this answer. Next, second part of the question, that it is a proton. For a proton, mass of the proton is given to you as 1.675 into 10 raised to minus 27 kgs, right? So I'll get velocity of the proton will be h upon mass of proton into lambda, right? So you can substitute the values and get the answer. The answer for this sum should be: velocity of electron is 2.427 into 10 raised to 6 meters per second. Velocity of proton is 1.318 into 10 raised to 3 meters per second. Next, let's see another sum, guys. Calculate the momentum. Calculate the momentum of. Calculate the momentum of. First part of the question, an electron. An electron whose de Broglie's wavelength is 12 Armstrong units. Whose de Broglie's wavelength is 12 Armstrong unit. Second part of the question, a proton whose de Broglie's wavelength is 1.2 Armstrong unit. Whose de Broglie's wavelength is 1.2 Armstrong units. De Broglie's wavelength. De Broglie's wavelength lambda is given by the formula h upon mv. But we know that mv is nothing but momentum. Therefore, I can say de Broglie's wavelength is h upon momentum. Therefore, momentum is h upon lambda. Now, once I have the formula, then I can find out. I can say that for an electron, momentum of the electron will be h upon lambda of the electron. H is Planck's constant, which is 6.63 into 10 raised to minus 34 SI units. And similarly for a proton, momentum of the proton will be nothing but h upon wavelength of the proton. The answer for this sum should be electron. Momentum of the electron is going to be 5.521 into 10 raised to minus 25 kgs meters per second, and momentum of the proton is 5.52 into 10 raised to minus 24 kgs meters per second. Right? Okay, we'll stop this here for the day. Thank you very much.